The computer knows 8 instructions, each identified by a 3-bit number called the instruction opcode. Each instruction also reads the 3 numbers after blah blah. So the program 0, 1, 2, 3 would run the instruction whose opcode is 0, pass it the operand 0, then run the instruction having opcode 2, and then pass the operand 3, then halt. There are 2 types of operand. Each instruction specifies the type of its operand. The value of a literal operand is the operand itself. For example, the value of the literal operand 7 is number 7. The value of a combo operand can be found as follows. Combo operand 0 through 3 represent literal value 0 to 3. Combo operand 4 represents the value of register A, 5 register B, 6 register C, 7 is reserved and will not appear in valid programs. Wait. Each identified by a 3-bit number called the instruction opcode. So 3-bit is 0 to 7. Okay, so these are the opcodes. The 8 instructions, the 8 instructions are as follows. The advanced instruction opcode 0 performs division. The numerator is the value in the A register. The denominator is found by raising 2 to the power of the instructions combo operand. So an operand of 2 would divide 2 by 2 to the power of 2. An operand 5 would divide A by 2 to the power of B. Okay, because it's register B. Okay. The result of the division operand is truncated to an integer and then writes to the A register. The BXL instruction opcode 1 calculates the bitwise OR of register B and the instruction's literal operand and stores the result in register B. Okay, the BST instruction calculates the value of its combo operand modulo 8 and writes that value to the B register. Does nothing if A register is 0. However, if the A register is not 0, it jumps by setting blah blah blah. Okay, we have all these instructions. If register C contains 9, the program 2.6 would read the program 2.6. So 2 is BST. So 3 lowest bits. So 2, 6. Wait. It's opcode 2 and 6 is register C. Calculates the value of its combo operand modulo 8. Okay, combo operand is whatever is in register C. Okay, so 9 modulo 8 is 1. Okay. If A... Okay, blah blah. The storage strange device has finished initiating its debugger and it displays some information about the program is trying to run your puzzle input. For example, to do this, initialize the register to the given values, then run. Okay. So I guess we're writing like a simple CPU here. What day was that? I don't even remember. It's the third element. Dot split. Okay, dot strip. Dot split. And add index 2. Convert it to an integer. And it's basically the same thing with A, B, and C. And then after that it's the program, so I just read line one time and then read line. The next one is the correct line. You split it and then take the second one, the first one, index 1, whatever. So that gives me my program. And then I want to split at commas. Zero, 1, 5, 4, 3, 0, perfect. And I kind of want to convert it to integer, so we'll take this for x and this. Perfect. So instruction 1 calculates bitwise OR of register B, bitwise XOR register B and the instruction's literal operand, and stores the value in register B. Okay, is there an example of 1? Five zero 5 1 5 4 0 1 5 4 3 0. Okay, 1 7. Okay, so if register contains 29, program 1 7. So 1 7 is BX bitwise XOR. So it's 26 XOR 7. Oh wait, is reserved and will not appear in any valid program. Oh. Wait, does that mean that 1 7 just means that it's literally that value? It's the wait, the value of literal operand is the operand itself, for example. The value of the literal operand 7 is the number 7. Okay. So 1 7 would be 29 XOR 7. So 26. Yeah. Okay, so the program goes left to right. Counter is equal to 0. Okay. Switch cases. Fuck it, I guess we're doing else if. So, okay, opcode starts at 0 and goes to 7. So, I guess we're doing this. Time to copy paste. 2, 3, 4, 5, 6, 7. Okay, opcode 0, what does it do? Advance. The instruction performs division. The numerator is the value in A register. The denominator is found by raising to the power of the instruction combo operand. Oh fuck, okay, so yeah, well, so I want to make a function called combo, I guess. So then the combo operand, you give it a code, and that also is a function. I mean, depending on which one it is. So 0 to 3, so I can cut these cases. Okay. Okay. So this is just code. Yeah, whatever. Okay, so 4 is register A, so return A. 5 is register B. 6 is register C, and 7 is reserved, and so it doesn't exist. Okay. So if the opcode is 0, it's division by 2 to the power of whatever. So it's just the it's a right shift, right? Yeah, right shift is division. So then it saves it in register A. So A is equal to okay, so A right shift by the combo operator. It'll be a right shift combo operand of okay, yeah. Once we got the opcode program counter, this goes 1. Yeah, so the operand of the program counter. I think at the end of all of these, program counter also increases by 1. Register B with the literal operand. So B is equals to B XOR, I guess here okay, just the XOR calculates the value of its combo operand modulo 8. So modulo 8. I mean, I could just do modulo 8, but I think bitwise it doesn't really matter. Modulo 8 is keeping the last 3, so I want to do like a bit mask. So bit mask would be okay, just 111. So the bit mask is 111, which is 1 plus 2 plus 4, so it's 7. So you do an AND. To the B register. So B register is equals to combo operand modulo 8, so it's AND 7. Wait, 1 1 1 1 3. So yes, it's 7. Yeah. Opcode 3 does nothing if A register is 0. However, if the register is not 0, so if A is not equal to 0, it jumps by setting the instruction pointer to the value of its literal operand. the instruction pointer to the value of its, by setting the instruction pointer to the value if this instruction jumps. Wait, what? If this instruction jumps, the instruction pointer is not increased by 2 after this instruction. So let's have an example of code 3. Oh. The program 015430 would output and leave 0. Okay, so wait, what are these? Zero, one. So divide A by 2. Oh man. Whatever, I'll just, by setting the instruction pointer. Okay, 0, 1, 3, 0, okay. Wait, doesn't it just make like an infinite loop if you do that? BXC operand 4 calculates the bitwise XOR register B and register C, then stores the result in register B. For legacy reasons, this instruction reads an operand but ignores it. Okay. The out instruction calculates the value of its combo operand modulo 8, then outputs that value. If a program outputs multiple values, they are separated by comma. Okay, so let's have output equals this, and then for 5, combo operand modulo 8, so it's and so big mask 7, and then output dot append output 6, like the advanced instruction. So that's division, except that the result is stored in register B. The numerator is still read from the A register. The numerator is still read from the A register. Okay. And then the final instruction, C register. Okay. Wait, why is this all indented? Okay, like this is better. And then I want to print let's run these small cases. So register C contains 9 and the program is 26. Oh, we're cooked. Oh, combo operand here. Then the register B would set to 1, okay. If A contains 10, program would output, okay. Oh, man. 505154, what does 5 do? Okay, so it appends modulo, the last 3 bits. Wait, sequence. Okay, because outputs is it's all integers. So when it joins, it can only join a string. So I guess when you append, you convert into a string. Zero, 1, 2. Okay, that's perfect. If A contains 2024. Four, 2, 5, 6, 7, 7. Okay, perfect. Oh, and leave 0. Okay, and 0 in register A. Perfect. Okay, your first task is to determine what the program is trying to output. To do this, initialize the register and run the given program, collecting any output produced by out instruction. Always join the values produced with commas after the above. Halt, its final product would be okay. Yeah. Using the information provided by the debugger, initialize the register to the given values. Then run the program. Once it halts, what do you get if you use commas to join the values? It outputs into a single string. Okay, so you want to run this program here. So you just skip this. Okay. So now we're in part 2. Digging deeper in the devices manual, you discover the problem. This program is supposed to output another copy of the program. Unfortunately, the values in register A seems to have been corrupted. You'll need to find a new value to which you can initialize register A so that the program's output instruction produces an exact copy of the program itself. For example, register A, B, C. This program outputs this program outputs a copy of itself if register A is instead initialized to this. The value. What is the lowest positive initial value for register A that causes the program to output a copy of itself? Oh, what the fuck? What is the lowest positive initial value causes the program to copy? With with linear search, I mean, linear search feels pretty troll. Is there a way to binary search it? So whenever you output, it's always gonna be the combo operand, the last 3 bits of the combo operand, and so you want it to be a copy of itself. 2415750 blah blah blah. Okay, so let's have this program here. So that's our program, and we want to output a copy of itself. Let's write down what it does. So last 3 bits of the combo operand, 7. So the combo operand is 4, and 4 is register A. So you're gonna set the last 3 bits are register A. So B is equals to A and oh my god, how do you draw and 1 1 1. So that's what the first one does. And then 1 5 1 5 B XOR the operand. So this does B is equals to B XOR operand. So this one B XOR operand is 5. So 5 is 0 1 1. So that means flip the last 2 bits of hello. Okay, so B is equals to B flipping the last 2 bits. So how can I write this? B flip last 2 bits. I'm doing Advent of Code Day 17. So 7 5. Divides sets C to A, right shift by the combo operand, which is 5, and that combo operand 5 is register B. Okay, then the next one 0 3 0 does the division, so A equals to A, right shift, combo operand 3 is just the value of 3. And then you got 4 1. Wait, so which one prints? Oh, it's opcode 5 that prints. Oh, but there's probably a jump, so here the print happens like here. Okay. Oh, and then this makes it restart I see. For which one? 1, 2, 3, 4, 5, 1, 2. Okay, so 4, 1, 4. We're doing X or B, X or C. So B is equals to B, X or C. Oh wait. Yeah, it's always C. Okay, 1, 6. So it's B equals 2. So we're at 1, 6. Right? Where am I trolling? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So sixth one is 1. So it's yeah, B XOR operand. So it's B XOR 6 is wait, 1, 2, 4. So it's 1, 1, 0. So flip first 2 bits. Just write it B XOR 1, 1, 0. And then this one I should write last 2 bits is B XOR 0, 1, 1. And then this operation 5, 5. So this would be output, or yeah, output operand. So it's a literal operand that you want. Oh no, it's a combo operand. So combo operand 5 is register B. B, and you want the last 3 bits. And then 3, 0, it means jump to 0. And then redo. So this is while A is not equal to 0. We repeat these steps. So can I simplify this equation? Okay. So then the first 2 steps can be simplified to B is equals to A and 1, 1, 1. So last 3 bits of A, and then you flip the last 2 bits. Okay, and C is equals to A shift B. So C is equals to A shift by this amount. So this is so it's a flip the last 2 bits of, so it's 1. So what this does is you have the last 3 bits of A, you keep 1 and you flip the last 2. So here's C, right shift B, so it'd be A ampersand and 1, 1, 1 XOR 0, 1, 1. And here you have A is equals to A right shift 3, b is equals 2, b, what the fuck, it's getting so cancer. So this is b. And then you XOR it with C, which is now this. And then you do b is equals to all of this thing. And then you XOR it with 110. And at the end you output the last 3 bits of B. Oh man. What does this do? Takes the last 3 bits of A and only flip the last 2. Okay, and then this A and then you want to output whoops. Man. Okay, so I know that A gets right shifted by 3 every time. So if A gets right shifted by 3 every time, it should get down to 0. Wait, so how many outputs do I want? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it has to be able, A has to be able to right shift 3 times, 16 times. So times 16. So that's equals to 40. What, 48, 30, 18, 48, yeah. So A has to be, wait, so it'd be like, if I have 1 and I right shift it 1 time, it gives me 0. This takes 2 times to right shift. So if A has a dominant bit at the 48th position, and then the rest can be whatever. So then that's 2 to the power 48 at least. Wait, 1, 2, 3, 4, 5, 6. So what's 2 to the power of 6? Oh wait, there's no way. Oh no, to the power of 6 times 3. Okay, and then 100k. Yeah, so it has to be between this and yeah, between this and 2 to the power of 6 times 3. So the worst case is no. So if it has 48 bits, so it'd be 2. Okay, yeah. So it'd rather be, it can be shifted by 3 6 times. So then this should be +1 -1. So this is the upper bound. And then the lower bound would be 2 to the power of 6 times 3. Is that right? Wait. One, 2, 3, 4, 5, 6. It gets shifted by 3 6 times until it hits 0. Okay, but it's 3 at a time. So since it's 3 at a time, so here instead 3 times 6, 18. So at the before last shift, it's 15. So A must have at least 16. Bits, because else we would have cleared it on the 5th one, right? Yeah, 3, shift. So I keep shifting to the right. If we do it 5 times, then it's gone. Okay, so it's at least 16 long. And at most 18. Yeah. So it's at least 16 long, at most 18. So 2 to the power of 16, 65k, and 2 to the power of 18. So it's between 65k and 262k, which confirms this hypothesis. But linear search would take forever. Because in my case, it's instead of 16, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's 3 times 16, which is 48. And it has, so that's at most. And the minimum would be minus 2, so 46. So how many, what's the range between that? 2 to the power of 46, 48, 2 to the power of 46. Oh my god, yeah, it's a huge number. Okay, so we know what we output is relative to A. Does C even matter? Well, C is a function of A. And C is only used here, and we can replace it with A. So every time we're going to output this equation, and we expect to have 2, 4, 1, 5, 7, 0, 3, okay. So we want this to be equals to 2. So all of this, it could be anything as long as the last bit, no, not the last bit, the second least significant bit is 1. So that, I guess I would narrow down my search. So it has to be between, the answer has to be between 46 and 48 bits. And oh no, it's the output of all of this shit. So output of this shit has to be 2 for the first one. I guess I could put this in an operation. Oh wait. Oh fuck. I'm solving Advent of Code Day 7 Part 2. So this would be there's XOR. No, XOR is commutative. If I flip them, it wouldn't change anything to the result. So this would be the last 3 bits of A, and then you flip the last 2. This is shifting A by the last. Oh, okay, this is a recurring thing here. And these two. Okay, because this is probably like. Okay, that's B and C. B XOR C, and then B XOR 110. Last 3 bits of A, and then you flip the last 2. A gets shifted by the same result here. So this is so you have the last 3. So let's call the last 3 bits of A, we can call them A. And what we actually want here, this would be A, and then flipped A's. So I could kind of say so this operation here would be A hat XOR A right shift. Oh my god, so this is kind of confusing if I call it A. Let's just call them X. So you have XXX. Just call them X hat. Yeah, so X hat X hat, which is this XOR A right shifted X hat, and then XOR 110, and then the last 3 bits. Oh man, I don't know what to do. Oh wait, but XX, they're not equal, so this should rather be XY0, let's call it XYZ. So it really depends on these values here. And the first one, we want it to be equal to 2, so 2, 0, 1, 0. Oh man, that's so cringe. So this, I don't think, I'm trying to, I guess what's the problem here is I'm trying to solve it mathematically, but maybe it's supposed to be solved programmatically. Man. Oh, this shit's hard, man. Is there a way to narrow down my input space? My search space, I mean. What, is there a way to binary search this? I know the bound is between this. How would I go about binary searching this? I'd try a value, and then how do I know if it's too big or too small? It's gonna be outputting me this thing. I don't think I can binary search this. Man. One, 2, 3, 4, 5, 6, 7, 8, 9. But I'm looking for 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I said the minimum was 2 to the power of 6. 2 to the power of 46. Oh man. How do I not get it rounded? Okay. 2 to the power of 46. What? Oh, it's. Oh, how do you. Wait, how many bits are in it? It's 64, right? Whoops, it's one left shifted 46 times. Okay, so this is the number. This should give me 16 instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, so that gives me 16. Let's do it, make it one less, so 4, 63, and this should give me 15 instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Wait, what? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, one. Oh man, I'm cringing, man. That's not the lower bound then. Oh, the lower bound is what, to the power 45 plus 1. Oh wait, it's getting right shifted 3 times 16, which is equals to 48. So it's 48 long. There'll be none left. Before 48 would be 45. So if it's 45 long, it'd be too short, because after 15 instructions you'd have 0 left. Alright, so let's try it to the power 45. I expect this to give me 15 instructions. Wait, still 16. What? Huh. Oh my god, am I trolling? Yeah, A gets right shifted by 3 every time. So if it's 3 long, it should just be 1 instruction. So 3 long be like 1, 1, 1. Oh wait, if it gets shifted 45 times, it means there's 45 zeros after it, so it'd be 46 long. So 45 would be actually 46 long, so if you do -1, then that would give me the correct one. So this would give me 15 instructions. Yeah, that would give me 15 instructions. So that's at least, that's 46 long still. So it's at least 2 to the power of 46 still. 48 long would be right shifted by 47 times. So that should give me 16 instructions. But if you have 48 minus 1, so that'd be the upper bound. So this should still give me 16 instructions. But if I plus 1 it, then it should give me 17. Yeah. So the upper bound is 2 to the power of 48 minus 1. So that's a search space. Okay, let's try this then. We're gonna try to predict the first output, and the first output oops. We said it was gonna be A, and 111 is 7, XOR 011, that's 3, XOR A right shifted by A and 7 XOR 3, and then all of that XOR 6 and 7. The keyboard sound and the speed at which you type sound like a typical C++ competitive programmer. Plot twist, you're using Python. Man, I'm in pain. So, oh my god, why isn't it working? So the prediction is wrong, but is it because of order of operations? XOR this, I think it's order of operations. Maybe if I just put all of these in parentheses. Okay, here I predicted 5, but it's wrong. So, is my equation wrong? Why is it wrong? Yeah, what's the progression of C? C is A right shifted by B at this point. Oh man. Is it right shift? It has A right shift, A and 7, XOR 3. I don't know, maybe we try parentheses. I'm desperate. No, it's so wrong. Okay, so let's recheck my equations. Two for opcode 2, b is equals to combo operand of 4, which will register a. Okay, so let's register a and 7. So and 7. That's good. And then second one, 1 5. 1 5 is b is equals to b XOR the operand, which is 5. And that's not 5, fuck. 5 is 1 0 1. So this is 1 0 1. I think that's the only mistake. Okay, so what does 1 6 do? Okay, 1 6, and then wait, what? Four one is B XOR C. Yeah. And 1 6. Oh wait. Okay, no, that's good. Opcode 1 means B XOR the operand, which is 6, and 6 is 1 1 0. That's right. So I made a mistake here for this one. So how does it tunnel? How does it chain? It chains into this one. Chains into this one. Okay, so it predicts correctly now. Let's try another random number. Okay. So let's find, oh no, finding all the A's that would give me that is gonna be so cock and ball torture. So these are the bits that I flip. So let's say that x, y, z goes last 3 bits of a. So then this is x, y, z. You have x hat, y, z hat. XOR a shifted by x hat, y, z hat. Oh my god. Okay. And then XOR 110. Ampersand. Okay, so at the beginning we want it to be equals to 2. So equals to 2 would mean 0, 1, 0, or like So if you remove this and here, you could say that this is equals to anything. If you have to flip the first 2 bits at the end, these 2, then we can reduce this one again. Wait. So this here was 0, 1, 0. But if you flip the first 2, it becomes 1, 0, 0. Let's move this around. A gets shifted by a certain amount, so we know that x hat, y, and z is between 0 and 7. So all the cases, what are all the cases? So you have either a shifted by 0 and 0, 0, 0. Okay, that's impossible. Wait. So it was what 0, 1, 0 was what I want at the beginning. This I can also, instead of calling that, I can call that what? Alpha, beta, gamma. I don't know, epsilon. So this would be alpha, beta, epsilon. And then here I flipped the first two. So that means I flipped none of them. So that's equals to x, y, z. Oh wait, so this is assume. So that would also mean that x, y, z is equals to, whoops. One, zero, one. So if the last 3 bits okay, so that's the first case. The second case is x hat, y, z hat. Let's go 0, 0, 1. So then you'd have a. Shift by 1. And then 0, 0, 1. No. Wait. So the equation would be oops. Yes, it'd be wait, let's take this off again. So then a whatever 1 1 x or 1 0 1. So we can reorder this, I guess. Oh, wait. So this flips the first two, so I can use commutativity and associativity. And then this flips the first two. So flip the first two. Gives me this. If X, Y, Z, K. One zero one is 5. One one, that's 3. Oh, whoops. 101 is 5. This is 3. No, I'm saying that this equation is reduced down to this. Wait. Okay, yeah. XYZ1. Oh, what the fuck? Okay, it's just this has to go first. Okay, works. Seems to work, yeah. So then for 0, so we're doing it XYZ to X bar YZ bar mapping. So 1, 0, 1 is 5. Alright, so let's make a table. One, 0, 1 is 5. 0, 1, 1. 0, 1, 1 is 3. So that's what 1, 0, 1. 1. Wait, that's 1, 0, 0. So that's 4. And that's 0, 1, 0. So that's 2. One, 1, 1, that's 7. And that's 0, 0, 1. One, 1, 1, 0. That's 6. And that's 7. No, it's 0. Five, 4. Zero, 0, 1. And this is 1, 1, 1, so that's 7. is 6. Zero, 1, 1 is 3. 1, 0, 1 is 5. It's 2. And this is 4 plus 2. Okay. I think we can reconstruct. Okay, so I think it's using this, we can reconstruct the input that would work. So we want this program. Oops. any of them equals to 2. Oh man. Wait, so does that make it into a DFS now if I have this as a clue? So after I shift it to 5, it means that these 5 numbers are discarded. You're reading these 3 here. And then you're flipping these 2. And this has to become 2. Okay, so maybe that's it, huh? Hmm, 48 at most. Wait, so that all depends on the last the last 3 digits of A. If the last 3 digits of A is 0, then this, or this, or this, or this, or that. Fuck, okay. So I guess we would start with answers equals to -1 times 48. So these are the bit positions for, yeah, that'd be the position of every bit. And then I think you would DFS to that with all the possibilities. Okay. So in the DFS, I have all these possibilities. So it's 0 to 8, 0 to 7. And I want to convert that 0 to 7 to binary. And then put it inside. Okay, so how would I go about that? So it's increments of 3, so 0, and then it's going to be 3. And it kind of puts them like that. The second bit. Oh wait. Okay, yeah, I'm kind of like thinking about the right to left, but it's the same thing. Yeah, I just gotta invert it at the end. A we shifted 5 times, and it's relative to program counters times 3. We shifted 3 times, and we expect it to be okay. So then this should be like this. And then okay, yeah. Wait, I should have it chunks of 3 instead. Since it's B16. No, that doesn't work actually. Because I need to move in discrete steps of 5. At the other specific index, I want to set them so it'll be at I. Okay. Okay, we're gonna set the bits here. And then here, uh, 101. 101 is 5. Oh. We're gonna set it to program counter. program counter, and then XOR this value, which is XYZ, XOR 0, 1, 1, which is 3. No, this only works for this specific program. So if you set the bits X, Y, Z to this, then we expect the ones at this offset to be equal to this. So the program at PC XOR 011, which is 3. It didn't even work. So we're saying that if the last two digits are 0, one, two, three, four, five. So these ones should be 2. 2 is 0, 1, 0. And 0, 1, 1 would become 0, 0, 1. So that's what 1, 2, 3, 4, 5 to the power 5. 32. Okay, so that works. It just means my program is poorly written. What if I added a 1 here? That's 32 plus 16. 16 is 48. Yeah, that also works. But then this would no longer work. Yeah. Let's say that the last 3 numbers were 0, 0, 1. Just shift to 4. Two is 0, 1, 0, so this would be 0, 0, 0. So if it was 1, I'd be able to get 2. Yeah. And what if it was 1, 0, 0, 1? So that's 1, 2, 4, 8. So that's 9. 9 also gets me 2. Yeah. So I want to set the bit at program counter plus 4, 0, 1. So that's 5. 1, 0, 1 is 5. The value that I want to set is the value at the program counter. XOR 0, 1, 1, that's 3. 053 142 506. That's good. Okay, that's why. That's what 1 0 1 0 1 1 0 0 1 2 4 8 16 32 30 40 44. No, that doesn't work. Okay, let's do a little test. One zero one. One zero one. Oh, okay, there's no times 3 here, it's just at index. The fuck? So I said for 0, 0, 0, you have 2 empty ones, and then here it'll have to be for 2. Since you're doing this, 2 would be 0, 0, 1. Skip 1, 0, 0. Okay, the first one, this is PC times 3. This is also PC times 3. Fuck. Zero, 0, 0, 1, 0, 0. Well, this one's the furthest we got. Two, 4, 1, 5, 7, 3. Oh, wait, what? 2, 4, 1, 5, 7. Okay, we got these ones. And it degenerates to 3, 5. Fuck. Wait. Which one was that? Five. 1, 2, 3, 4, 5. Okay, we got 5 of them. So I got 8 of them. One, two, three, four, five, six, seven, 8. It's able to generate half of them. But what does it fail after? Wait, 8 times 3. It's 27. It's 28. 24. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. You like the idea that I'm trying? I don't even know if you understand it. I barely understand what I'm doing. But I'm able to output half of the numbers correctly. So I think the idea works, it's just there's a problem in the implementation. I'm not sure why it's failing though. After 8, it's not able to. Not sure why. Man. I have depression. Okay, so I have this number. It can generate 8 digits. For this XYZ value. Well, the XYZ is the last 3 bits of A. So last 3 bits of A are values between 0. Oh, wait. You're right. 7 is not included. Fuck. Is that the missing link? Wait. I don't want to print all of this. Oh, still no solutions though. Man, I was hoping that would fix all my problems. 8 is still the longest I'm able to get. Is there something limiting how far it can go? Because let's say I'm at this one, this array, and then it's gonna try to wait, if PC equals the length of the program, what's the length? No, you're not reaching the length of the program. It means it's failing all of them. Why does it keep failing? Okay, let's try something like so what do we see here? So let's see at 8. It fails for both of them. 0. So if PC is 8, it should be trying to insert at index 24. Yeah, so it's index 24 that should be trying to input its value. And then why is it failing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so it's trying to insert into that, but it's failing. So let's do a little test here. So I have an array, and it's this one. And then what I'm trying to do is set bits. Let's say I'm setting, so it's at index 24. The value I'll put like 0 for this array. And this is if it succeeds. Print array and success. So it fails. Okay, so then that's probably a mistake in my implementation of set bits. So 0 to 3. If index times I. Oh, I'm trolling, it's plus I. So now it succeeds. Oh my god. Okay, so maybe that's gonna work. Man, still doesn't work. Wait. Okay, it goes up to 15. Oh, I was thinking about that. This could be an edge case actually when it reaches this point. But 15 is pretty close. There's something off still though. Let's see if the claims are true. So this one claims to go up to 15. So I have this test array. Wait, why do I have so many -1s here? So let's check one that claims to be able to generate 15. Okay, it's this one. This one claims to be able to generate 15. Let's run part 1. 2 4 1 5 7 5 0 3 4 1 1 6 5 5 3. Oh, so close. Okay. Man. So why is it not able to hit the 16th bit? So we're at 15 here. 15 times 3 is 45. I know this is length 46, so index 45 is here. Oh, okay, so this is the problem when you're trying to insert the bits here. Wait, it's no, it's length 48 it should be, actually. Okay. Should be length 48, right? Because here it's length of the program times 3, so that's 48. Just to be sure, I'll print it. Yeah, it goes up to 48, or rather there should be the length of my array, which is the array that I dump inside DFS. Okay, I'm just dumping a random array here. No, I'm just making copies all the time. But yeah, I mean, it should be that length of program times 3, so that's 48. So because if it has 49 bits, it's gonna start generating a if it has 49 bits, it's gonna generate a 17th instruction. So what's 2 to the power 49? I just want to confirm that to be sure. So print 2 to the power of 49. Wait, 2 to the power 49. Wait, 2 to the power of 1 is 2 digits. So it'd be 2 to the power 48 creates 49 digits. So in theory, this should generate 17 commands. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Rather, I should just print the length of the output. Or, fuck. It should be in part 1. Okay, length 17, but if I subtract 1, then this creates 16. Yeah. So it has to be 48 bits. Up to 48 bits. So it needs to be able to fit within my an array of size 48. So if I try to set a bit outside of that range, so index plus I is greater than or equal than the length of the array, then that's not good. Fuck. So close. So close. What's missing? What's missing? In theory, nothing should be missing. Wait, when I'm trying to place that last one. Because there's at the last step, there's gonna be 3 bits remaining. Okay, there's 3 bits remaining. And the instruction set says wait, if there's 3 bits remaining, we can only shift up to 3. Not even. If there's 3 bits remaining, how many shifts can you make? Fuck. Oh, I see the problem. Because we're still able to set zeros even if it's out of bound. Okay, so I think that's the thing. So if index I plus 1 is greater than the length and the value that you're trying to put in. So the value that you're trying to put in is this one. Is not equal to 0. Then in this case you return false. If index plus I and the value is not equal to 0. I mean, I just want to return. Okay, yeah. No, because then I might. Wait. Well, if it's equals, if it's not equal to 0, then you want to return false. And then this is a case where I want to add it. But if it's out of bound and it is 0, so maybe I should just have 2 cases instead in this one. If it's equal to 0, then you don't need to actually set it, then you just continue. Okay. Will this work now? Okay, we have working solutions. Oh, now we find the minimum. Okay, so possibilities equals array, and then this is the conversion thing. So this is where I can convert it. Enumerate the array value plus equals no shift, and then we can take that value and add it into the possibilities. So then we can print the possibilities. I'll do possibilities.sort and then print possibilities. And this one is the smallest one. Okay, and then let's run part 1 to confirm. Two four 2415750341165. Let's go. I think we found it. Oh fuck, man, where's my browser? Let's go. Finally solved after 3 hours. Get me out. The issue was that when I was trying to insert bits within the array of size 48, the bit that you could insert could be a 0. And that special case where it's 0, you're allowed to go out of range. Because I had a check of if you're trying to set a bit out of range, then it just returns false. But that's not true, because a leading 0 doesn't count as an actual bit. Okay, fuck. Oh, that was pretty hype, man. Feels good. Feels good. The effort I took to do this fucking paint shit paid off. Oops. The fuck? Man, I'm shaking too hard. I'm too hyped. Whoops, that looks weird. Oh my god, it's not visible. Wait, what if I take all of this, I cut it? Okay. Oops. Take the bucket tool. Drop some white. And then I paste. Will that work? Man, I miss the old MS Paint. Okay, that worked. Okay, thank you for watching. I'm going to sleep. It's 4 a.m. where I live. Bye bye.